Hello, everyone. This is a review for the first quiz of the new semester. So let's just jump right in. So we started out the new semester by asking the question, why is water so quote unquote sticky when acetone, hexane, and alcohol seem not to be that way? Some examples we saw are that you can hold many, many more drops of water on a penny than you can acetone or hexane or alcohol. We also found that when you take a balloon and charge it and hold it up to water, it's able to make water curve and bend towards the balloon. And we looked at this idea that a paperclip could float on top of water, maybe a coin too. We also noticed that acetone and alcohol tend to evaporate more quickly than water does. So there's some sort of sticky force that's holding these water molecules together. What is that force? Well, the answer is essentially that water we found was polar. Not like a polar bear, but in a sense like a polar bear, because polar bears live in the North Pole. The Earth has a North and a South Pole, and that's similar to molecules, which also have a North and a South Pole, much like magnets. And we know magnets can be sticky, and North and South attract. Opposites attract, we know this. So water acts as a magnet, attracting and sticking other water molecules together. And polar substances in general tend to do this, whereas something like hexane, which we see on the right, does not have this sort of polarity, these secret attractions. So it tends to evaporate more quickly. So what makes water polar? So essentially, the difference in electronegativity is what is going to make it polar, because as we saw in the last slide, there's sort of two different regions of water. There's the hydrogen side of water and there's the oxygen side of water. And hydrogen tends to have this sort of blue color that we use as a diagram to show that it has a partial positive charge. And the oxygen, on the other hand, tends to have this negative charge. So that creates a magnet situation where a positive side is attracted to a negative side. Right? Why does water have a positive and a negative side? Well, hydrogen is at the very low end scale of electronegativity. That means it's not very electron hungry, whereas the oxygen is way over on the other side of the periodic table and the electronegativity scale, and it's weighing in at 3.44. It is very electron hungry. So the electrons tend to hang out more on oxygen. So that makes the molecule partially positive and partially negative. You do not see polar interactions happening when it's the same atom, because there's no difference in electronegativity, so they'll be equal. In something like HF, there would be a very big difference in electronegativity. So we would call that polar covalent. And finally, if two molecules are very close together, such as F, which fluoride, and C, chloride, if these two were bonded together, there's not much difference in electronegativity, 3.98 and 3.16. So there would be a pole, but not as much. And remember, polar, nonpolar, we're always talking about covalent molecules where the electrons are shared, as opposed to ionic bonds or metallic bonds. Okay, so that leads us to the question of how do we know if a molecule is polar or nonpolar? So here's an example of something we looked at. In this case, we have two atoms. The yellow atom is not very electronegative, and on the right, B, the green atom, is very electronegative. So we see that there's a bond dipole which points to the more electronegative side. And there are also little symbols, delta symbols, that show that there's the more electronegative atom has more electrons, so it's slightly negative, and the less electronegative atom has a partial positive. So rule number one is if you have two atoms and they're different in electronegativity, then it's polar. An example of that would be hydrogen fluoride. As we saw on this slide back, going in the wrong direction. As we saw on this slide back here, hydrogen 2.2, fluoride 3.98. There's a pretty big difference in electronegativity there. So this is a very electronegative, big electronegative difference. Fluorine is very electronegative. So this is a polar bond. Now, if they are the same atom and there's no difference in electronegativity, then it is nonpolar. So in this case, we have that the electronegativity is set to be the same thing for both atoms. It's both somewhere in about in the middle. But it doesn't really matter. They could both be more, they could both be less. As long as they're the same in electronegativity, then this molecule will be nonpolar. There'll be no bond dipole, no partial charges. It is non-polar. Now, what if there are more than just two atoms? Well, okay, an example of a nonpolar atom would be oxygen. Oxygen is a diatomic molecule. It's two oxygens bonded together with a double bond. So since these are both the same atom, oxygen, this is non-polar. Now, going back to what I was just saying, what if you have more than two atoms? Well, if there's more than two atoms, you have to look, is it at the, you have to ask yourself, is it asymmetrical or symmetrical? If it's asymmetrical, then it's going to be polar. What do I mean by asymmetrical? Well, symmetrical means the same on all sides. Symmetry, right? Like your face has symmetry because one side is the same as the other side, right? Unless you're two-face. You can flip this direction and this direction. So that's the mental test. If you can take a molecule and flip it around in your head, up and down, and it looks the same no matter what you do to it, then it is asymmetrical. So if it is asymmetrical, then the more electronegative atom, in this case it's B, is going to be the overall sum, right? There's two bond dipoles here that point in this direction and this direction. But when they, in a case where there's three atoms together, these two bond dipoles are going to join forces, and the net will be the overall dipole of the molecule, which would just go in straight up in this case. So if you, what does a nonpolar molecule with more than three atoms look like? Let's take a look. But an example of a polar molecule, this is our famous poster child polar molecule, would be water, right? Oxygen is very electronegative, hydrogen not very electronegative. So there's a positive charge on oxygen, or sorry, a negative charge on oxygen, and the molecular dipole points up. If there are more than two atoms and it is symmetrical, then it is non-polar. Because even though there might be dipoles, they cancel each other out, kind of like tug of war. If two twins were playing tug of war, the two would cancel each other out so that there is no polarity. Even if you have different atoms, it's still non-polar. There's no molecular dipole, there's no partial charges if it's symmetrical. In this case, I could flip the atom around and don't pay attention to the colors, but the overall shape would still be the same whether you flipped it up and down or side to side. So an example of a nonpolar molecule would be CO2, carbon dioxide, because there is a carbon, there's oxygens, those are different atoms, but it's symmetrical. Okay. So let me just so in summary, polar covalent bond means that electrons are not shared equally between the two atoms, but it could be more. So we'll say 2 plus atoms. So one atom is slightly negative in charge and one is slightly positive in charge. In non-polar covalent bonds, electrons are shared equally, so the atoms remain neutral in charge. So covalent compounds with polar bonds can be polar or nonpolar. It depends on the arrangement. Like I said, is it symmetrical or not? In this case, we have CO2, which is what we just looked at, and there are 2 bond dipoles, but they cancel each other out, like we said. But in the case of formaldehyde, which is a chemical that's used to embalm dead bodies to preserve them, there is a slight dipole because it sort of has a similar shape to water, just with a carbon in the middle. It's not symmetrical. It would be symmetrical if you flipped it this way, right? Still same shape if you flip it vertically, but if you flip it horizontally, it would look different. The oxygen would be on one side instead of the hydrogens. So that there's a net dipole there. So then after we learned those basic facts, we started looking at like how you can apply this knowledge to different real life situations. And we started with why the question of why won't water by itself take out a greasy oil stain? Water won't take out stains and it won't clean your food just by itself. You have to have what we call a surfactant, soap. So the answer that water won't take out a grease stain, water is polar. And oil, which tends to have a similar structure as propane, but just usually longer, more carbons, is nonpolar. So you need soap, which is a surfactant. And that's where Surfactant Man comes in. And he has a water-loving hand, which we call hydrophilic, and a oil-loving hand, which we call hydrophobic. So he's able to reach between the two and help join water and oil together. That's the way we use soap. It's one of the reasons we use soap to wash our hands. So in this case, you can see the oil. The oil's all here in the center. Okay. And then we have the water. So he's grabbing on with his hydrophobic hand, which would also be nonpolar. And then with his other hand, he's grabbing on to this water molecule, which is represented by a positive and a negative charge. So in this case, we have water. And he grabs the two, and the oil gets condensed into these small clusters. It gets trapped inside a sort of barrier of soap, sort of a soap bubble, if you will. And then the water contains that whole structure and is able to wash the oil away. And again, you can see on the left, this structure is very symmetrical. And on the right, it's not symmetrical. It's symmetrical left or right, but not top to bottom. All right, what are some applications that scientists use? Well, for one example we looked at is the mRNA that is the sort of genetic recipe that cells in your lymph nodes use to make copies. It's sort of like a little recipe to make spike proteins so that you can train your immune system. So how does your body know how to read those copies? Is uracil polar or non-polar? Well, if we look over on the right, this is the blue is the uracil molecule, okay? And that's this part of the code, right? That's the part that's going to get read. What do we see? Well, remember anywhere you see a line, that's carbon. This is a organic molecule, so this is all carbon. Well, we have carbon and oxygen. We have nitrogen and hydrogen. Nitrogen and carbon here, carbon and oxygen, nitrogen and hydrogen. So there's lots of differences in atoms. There's lots of differences in electronegativity. So it could be very well be polar, but the other question we have to ask is it symmetrical? And let's just get rid of all this stuff to look at it. Is it symmetrical? Is it the same on both sides? And we could say maybe it's a little symmetrical, like this side is kind of similar to this side, but not really, because you've got this whole thing going on. It's not really symmetrical. It's not the same on all sides. So yes, this would be a polar molecule. And the same would be true for any of these molecules down below. Thymine, guanine, adenosine, all of the nucleobases, all of the different genetic codes are polar. What's another application? We looked at this application. So since oil is non-polar, think about a bird, right? Birds are able to travel in the ocean because their feathers are specially designed to keep them from getting wet, right? What would happen to you if you jumped in the ocean in the middle of winter? You would freeze to death. You might freeze to death in the summer. The Pacific Ocean is always pretty cold where we live. You might see people out there surfing, but they usually have wetsuits on to keep them warm, right? So a bird's no different. They're also susceptible to the cold water. Okay, they do not want to get in that cold water, and they're smaller than us. It's harder for them to keep their body heat up. So if they were to get wet, they would die. So their feathers are non-polar. So that means that their feathers are specially designed to keep water off of them. They're hydrophobic. So feathers are also non-polar. That's really good for birds, but until there's an oil spill. So what's going to happen in an oil spill? Well, oil is also non-polar. So water may not stick to a bird's feathers, but oil is going to stick to their feathers really well. And that's why when these oil spills happen and environmentalists go out to try to save these poor birds, they're going to use like dish soap or some sort of soap that will dissolve that oil off of their skin. Finally, we looked at some case studies of other applications. So for example, when you smell something, your nose is able to tell what the smell is because your nose has polar receptor sites. So it's only going to recognize polar molecules. It does this because polar molecules can be dangerous, but they can also be tasty. So your body has evolved over millions of years to recognize and smell and quickly identify anything that is dangerous or tasty. So methane is something that our ancestors would not have come across. So they haven't evolved to smelling non-polar molecules such as methane. Remember, methane, its Lewis dot structure looks like this. Um, it's very symmetrical, so it's nonpolar. So when you turn on the little flame on your stove, this is what's coming out, and it's nonpolar. You wouldn't smell it if there was a gas leak in your house. So instead, we put this molecule, which is polar, because it is symmetrical going this way, but it is not symmetrical going up and down. So we put dimethyl sulfide in to manufacturers put it in so that it will keep you from getting sick. And you guys did a great job of presenting on that. Capsicum. Now, this molecule has some polar regions. When you eat spicy food, this thing tends to get stuck on your tongue, and it doesn't go away quickly because it's a little nonpolar. So you want to wash it away. These regions are all kind of nonpolar because they all look very similar. By the way, these are all carbons. So you want something that looks as close to capsicum as possible to dissolve it. In this case, that would be milk because it has the saturated acids as you guys presented. Although I will say that there are other factors to consider besides what will just dissolve something well, such as what will neutralize an acid, and also what is just a better absorbent material. So people say eat bread after you eat something spicy because the bread will like soak up the oils. All right, another case study we looked at was poison ivy. What would be the most similar in a very similar way, this material, soil laurelate carcinoate, but it's commonly known as Technu. It's a poison ivy remedy. I keep a bottle of it when I go hiking, just in case someone I know gets exposed to poison ivy. Although I personally am not allergic to poison ivy, I've never gotten it before. I did a fun thing in class last year where I brought some poison ivy in and then I rubbed it all over my hands. And people were like, "No, Mr. DeLow, don't do that. What are you doing?" I was like, "It's okay, guys. I'm not allergic to it." All right, finally, oil and water. They don't mix, but let's just watch. Oh, we skipped ahead. Let's start that over. A triglyceride is fat. It's nonpolar. Okay, so mayonnaise. If you've ever wondered how to make it, now you know. So we're looking at a fat molecule, which you can see on the left, very nonpolar in structure, and then a acetic acid, which has a polar structure, and then lecithin, which has two different sides. It's kind of hard to see, but one side is nonpolar, one side is polar, so it's able to emulsify those two ingredients together. All right. That's everything that the test covers. So good luck, and be sure to study, and I'll see you tomorrow.